Good morning, everyone. Welcome to day 2 of ECAI. Hope you all had a good night's rest. Our first invited speaker of today is Professor Ariel Procaccia. Ariel is Gordon McKay Professor of Computer Science at Harvard University. His work ranges for a broad and dynamic set of problems related to AI, algorithms, economics, and society. He has helped create systems and platforms that are widely used to solve everyday fair division problems, resettle refugees, mitigate bias in peer review, and select citizens' assemblies. We'll hear a bit about that today. To make his research accessible to the public, he regularly writes opinions and exposition pieces for publications in the general media, such as Washington Post, Bloomberg, Wired, and Scientific American. His awards are many and numerous and include the Social Choice and Welfare Prize, the Guggenheim Fellowship, ECAI Computers and Thought Award, and the Sloan Research Foundations. Ariel, the floor is yours. Thank you so much for coming.
Good morning, everybody. Thanks so much. I'm really delighted to be here in this beautiful conference center in this beautiful city. The topic of the talk today is democracy and the pursuit of randomness. And it's joint work with a couple of people. Bailey Flanagan, who's a fifth-year PhD student at Carnegie Mellon. Paul Gueltz, who's a former student hanging out at UC Berkeley this year and joining Cornell next year. Anupam Gupta, who's a professor at CMU, Brett Hennig, who's the co-founder and director of the Sortition Foundation, and Greg Kinney, another former student who's now at UT Austin. So I'd like to start this talk with a quote from Jean-Jacques Rousseau, who had this to say about early democracy in England. This is the early 18th century. He said that the people of England deceive themselves when they fancy they are free. They are so, in fact, during the election of members of parliament, for as soon as a new one is elected, they are again in chains and are nothing. So this is a pretty dramatic quote, but I think it still resonates with us today when we think about the challenges facing democracy, rock-bottom trust in institutions, difficulty to get stuff done even when there's consensus around the issues, and so on and on. But the question, of course, is what's the alternative? Is there a different way of doing democracy? And one possible answer is the idea of sortition, which is the idea of democracy built on lotteries instead of elections, or in other words, the idea of choosing representatives at random. Now, this idea may sound crazy if you haven't heard about it before, but it actually has a lot of historical precedent. It dates back to ancient Athens, where some of the main organs of government were selected by lot, or at random. During the Renaissance in Florence, in Venice, and the Kingdom of Aragon, which is part of modern-day Spain, again, some of the main organs of government were selected by lot. But sortition essentially disappeared during the American and French revolutions that made democracy essentially synonymous with elections. Today, it's very difficult for us to think about democracy without thinking about elections. However, sortition has been making a comeback in the last decade or so, especially in the form of citizens' assemblies, which are randomly selected groups of people from all walks of life, typically convened by local or national governments. And they meet to discuss important questions and typically reach decisions that inform policymakers. Now, a key aspect of these assemblies is deliberation. They meet over a period of weeks or months, and they spend a lot of time first being informed about the issues and then discussing the issues, deliberating. So this is really a crucial component, and one reason why this is thought as a form of deliberative democracy. Now, this has been happening on a wide scale around the world, so many dozens of assemblies per year. Let me just give you a couple of examples, and we'll see a few more examples later. So, a very famous couple of assemblies happened in Ireland in the last couple of years to talk about constitutional issues. And they famously led to the legalization of abortions and the institutionalization of gay marriage after referenda. So this was kind of very big impact due to these couple of assemblies in Ireland. In France, President Emmanuel Macron is a big supporter of citizens' assemblies. So, for example, in 2019 to 2020, they had a National Assembly to talk about climate change, which led to many recommendations. One estimate that I've seen was that 47% of the recommendations were adopted and became law. So that's, pretty good impact. Just recently, they finished another National Assembly to talk about end-of-life issues. And I think a very exciting trend that's happening right now is the idea of having permanent citizens' assemblies. So permanent not in the sense that they're selected forever, but they're a permanent institution, typically selected every year and a half at random. So a group of people selected every year and a half. And there's kind of a legal mechanism for the interaction between this permanent assembly and the parliament. So this model was first adopted in the German-speaking region of Belgium that has its own parliament in 2019. But since then, it's been extended and adopted elsewhere, for example, in Paris and Berlin, where the permanent assembly works in parallel to the city council. So I think this is a really exciting trend that really points the way forward for the future of sortition as kind of a permanent institution. Now, there's a lot to say about sortition and citizens' assemblies. There are many aspects of this process. In this talk, I'll just focus on one particular aspect, which is the process by which these assemblies are assembled, by which they're selected. So ideally, what you would want to do is if you have an assembly or a panel of K people, you would want to select these K people uniformly at random from the population. If you did that, that would satisfy a crucial property that's known as descriptive representation, which means that the assembly, the panel, represents the population across various dimensions. Gender, age, ethnicity, we'll see some examples later. And this property of descriptive representation is seen as a source of legitimacy and trust for citizens' assemblies. It's well studied that when people identify people who are like them on the assembly and see kind of the diversity of faces on the assembly, that really increases legitimacy and trust. So that's seen as a non-negotiable aspect of citizens' assemblies. The problem, of course, is that this process isn't feasible because you can't just take people from the population and force them to serve on the panel. So here's how the process works in practice. You start again from the population, but then you invite a subset of the population selected uniformly at random to potentially serve on the assembly. I'm referring to these people as letter recipients because typically the invitations are done by snail mail, but we've also seen, SMS messages, phone calls, or other methods organizations use to do the recruitment. Now, the letter recipients, these people who are invited, decide whether to opt in and whether to say, I will join the assembly if I'm selected. The ones who opt in form the pool of volunteers. And finally, the panel is selected somehow at random from the pool of volunteers. Now, the challenge is that while the set of letter recipients is representative of the population, because they were chosen uniformly at random, and that we want the panel to be representative of the population, the pool of volunteers is highly unrepresentative of the population because of self-selection bias. So to illustrate this, let's look at a particular example. This is from Climate Assembly UK, which, as the name suggests, was a national climate assembly in the UK that was organized by the UK House of Commons and was administered by the Sortition Foundation. So here the pool size is 1,727, out of, by the way, an estimated 60,000 invitations that were sent, so the opt-in rate is pretty low, and that's pretty typical for these national assemblies. And the panel size is 110, so we want to select 110 people out of the 1,727 volunteers. Now, what I'm showing you here is 7 features that the organizers cared about in terms of getting representation. So the features are gender, age, geography, that's the area in the UK, education level, ethnicity, area which is urban versus rural, and the final one is position on climate change, where the options are very concerned, fairly concerned, not very concerned, or not at all concerned. And for each feature, I'm showing you the distribution of feature values in the population and in the pool of volunteers. So I want to point your attention specifically to the education feature here in the middle. And notice that the people with the lowest level of education in blue are significantly underrepresented in the pool compared to the population. Whereas people with the highest level of education in green are significantly overrepresented in the pool compared to the population. Similarly, if you look at climate change here on the right, you can see that people are not very concerned or not at all concerned in green and red, have some representation in the population, but are essentially unrepresented in the pool of volunteers, which is not surprising, right? If you're skeptical about climate change, it's unlikely you would volunteer to spend weeks or months of your time deliberating a path to zero emissions in the UK. So given this picture, the question becomes, how do we choose a representative panel at random from this highly unrepresentative pool of volunteers? And the way this is done, invariably, is by imposing some kind of quotas on the feature values. So, for example, if we look at the education feature, and the people with the lowest level of education in blue, the proportional share of this feature value out of the 110 seats in this example would be 42, based on the representation in the population. And what we might say is we are willing to accept anything between a lower quota of 39 and an upper quota of 45. Similarly, for the middle level of education in yellow, the proportional share would be 39, and we might say we will accept between 36 and 42. And finally, for the highest level of education in green, the proportional share is 29. Maybe here we're a bit more stringent, and we say we want between 27 and 31. And similarly, we would impose these quotas for the feature values of the age feature and for the 5 other features that we saw on the previous example. But even with these quotas, of course, now the question becomes, how do we select a panel, a representative panel, at random in a way that satisfies the quotas from the unrepresentative pool of volunteers? And the way this was done before our work is using some kind of greedy algorithm. So we've seen a bunch of greedy algorithms used by different organizations. And I'm going to focus on a particular one, just to illustrate it, that was used by the Sortition Foundation before our collaboration. I'm going to illustrate this algorithm on a toy example. So in this example, we have a pool of 20 volunteers that are identified by 2 features: shape, either star or heart, and color, either blue or green. The panel size is 10. We want to select 10 out of the 20 volunteers. And for simplicity, we'll just have lower quotas in this example. Over here, so we require at least 4 stars, 4 heart, 4 blue, and 4 green. Now here's how the algorithm works. So at every stage, it computes the need of every feature value, where the need is the ratio between the number of people we still need to recruit with that feature value and the remaining number of volunteers with that feature value. The algorithm then identifies the feature value with the highest need and selects uniformly at random among the remaining volunteers with that feature value. So let's illustrate this on the example. Initially, the need for star is 4 over 10, because we have a lower quota of 4, and we have 10 stars in our pool of volunteers. The need for heart is also 4 over 10. The need for blue is 4 over 11, and the need for green is 4 over 9. So the highest need is for green, and what we do is we select a green person uniformly at random from the pool of volunteers. So I'm showing the selection over here using this yellow highlight. I've selected a green person at random, supposedly. This green person also happens to be a star. So now I need to update the need for green and for star. So the need for green is now 3 over 8. We need 3 more. We have 8 green people remaining in the pool of volunteers. And the need for star is now 3 over 9. After this update, the highest need will be for heart. So we choose a heart uniformly at random, shown over here, and we update the need for heart and for blue. So we got this new vector of needs. At this point, the highest need is for green. So we select a green person and we update. Highest need is for heart. So we select the heart and we update. Green and update, heart and update, green and update, and heart. So of course you weren't meant to follow these last calculations, but you can work it out and see that you get the sequence of green heart, green heart, green heart, green heart. So far we've selected 8 people for our panel, and notice that the panel already satisfies all of the quotas. It already has 4 stars, 4 hearts, 4 blue, and 4 green. We have 2 more seats remaining on our panel, and we can now go ahead and select the last 2 people uniformly at random from the remaining volunteers. Now, I want to point your attention to this blue star over here. And notice that this blue star had a much lower chance of being selected than the other volunteers. Because again, we chose green heart, green heart, green heart, green heart. The blue star had no chance of being selected until the very last 2 steps of the selection process, and overall has a much lower chance of being selected than the other volunteers, which seems unfair to this blue star. Now, this issue of fairness is another central issue in citizens' assemblies and sortition. Political philosophers talk about this idea of equalizing selection probabilities as something that realizes ideas like equality of opportunity, equality of participation. Of course, it's not possible to exactly equalize probabilities, but then the ideal is getting as close as possible to achieving equal selection probabilities and having everybody participate with an equal chance. Okay, so this is another central criterion for sortition, another source of its legitimacy, and it seems like this is badly abused in this particular example by the algorithm. Now, you might say, well, maybe in this example, this is unavoidable because of how I set the quotas, how I constructed the example. And we'll see in a few minutes that that's not the case. This is completely avoidable in this example. Now, you might also wonder whether this is something that only happens in this toy example and doesn't happen in real life. And it turns out it very much happens in real life as well. So to see that, I'll show you this figure, which is the result of running the greedy algorithm many times, again on the Climate Assembly UK data, or running example. And what you're seeing here is the histogram of selection probabilities for the different volunteers. And in particular, if you look at this bar over here, what this says is that around 450 volunteers, so more than a quarter of the volunteers, have selection probabilities that are very close to 0. And in fact, for many of them, it's even closer than what this bar would suggest. Okay, so this says that even on this real-world example, many of the volunteers are essentially excluded from the selection process. Now, you might again say, well, maybe this is unavoidable in this example because of how the organizers set up the quotas. And again, that's not the case. So this is the result of running another algorithm that for now I'll refer to as the mystery challenger on the same data. And what you can see is that even the minimum selection probability, represented by this bar, is nicely bounded away from 0. Right? Which means that everybody has at least a reasonable chance of being selected. Nobody is excluded from the selection process. So this seems much better than the histogram at the top. So the question, of course, is how do we get from the histogram at the top to the histogram at the bottom? And the answer, which probably wouldn't be very surprising to many of you, is that instead of running a greedy algorithm, we optimize directly over the distribution over possible panels. So what do I mean? Let's go back to our example, the toy example from a couple of slides ago. And remember that I promised that on this example, we can do much better. We can avoid the unfairness. So what I propose is the following. We'll run the following lottery, where with probability 1/2, we select the first and third rows of volunteers. And with probability 1/2, we select the second and fourth rows of volunteers. Notice that each one of these panels satisfies ex post the quotas. Each one of them has 4 stars, 4 hearts, 4 blue, and 4 green. Moreover, when I run this lottery, when I select each of these panels with probability 1/2, I give every volunteer probability of exactly 1/2 of being selected. So this exactly equalizes the selection probabilities for all volunteers and satisfies representation, satisfies the quotas. Now let's spice things up a bit by increasing some of the quotas. So I'm going to increase the quota on star to 6 and the quotas on blue and green to 5 each. With these quotas, I claim that now the blue star actually has to be deterministically selected. The reason is that if I don't select the blue star, the quota of 6 stars mean that I have to select 6 of the green stars. But then I have only 4 remaining seats on my panel, and I won't be able to satisfy the quota of 5 on blue people. So the conclusion is we have to select the blue star, but subject to that, we have quite a bit of flexibility in doing the rest of the selection. And what I propose is that in addition to the blue star, we will select 5 of the 9 green stars uniformly at random, and 4 of the 10 blue hearts uniformly at random. This gives me a distribution over many, many possible panels, each of which is selected with very small probability. But the important thing to note is that the individual selection probabilities of the volunteers are actually very significant. The lowest selection probability of any volunteer is that of the blue hearts, which are selected with 40% probability, right? So pretty good probability. So in this example, because of this constraint with the blue star and the quotas and the symmetries, this seems like the most reasonable thing you can do in terms of getting as close as possible to equal fairness probabilities. But of course, what we would want is an approach that works much more generally, that can take any instance of a problem and give a fair solution in some sense. And in order to do that, we draw on an area that's very close to my heart, called fair division. It's also quite nicely represented here at ECAI with a bunch of papers. What fair division does is it thinks about algorithms for fairly dividing stuff. And to think about our problem as a fair division problem, we think of a distribution over panels of size k as dividing the overall selection probability of k between the pool members. In other words, we have a divisible resource, which is the overall selection probability of k for the k seats. And we think of the players in our instance as the pool members. The utility of a player here is their probability of being selected, which they want to maximize. Okay, so this kind of maps this to the fair division terminology. And using this connection, we can now adopt ideas from fair division and apply them in our setting. So that allows me to unmask the mystery challenger. This is a mechanism called Leximin from fair division, which is known to have really good properties in various domains in fair division. What it does is it maximizes the minimum utility of any player. Subject to that, it maximizes the second lowest utility. Subject to that, the third lowest utility, and so on. What this means in our context is that it selects the distribution over quota-compliant panels that maximizes the minimum probability of any volunteer of being selected. Subject to that, maximizes the second lowest probability. Subject to that, the third lowest, and so on. And when we run this on the climate assembly UK data, we get the histogram that we saw before. Now, another natural option is Nash welfare, which is the mechanism that maximizes the product of utilities of players. Again, in our case, a distribution over quota-compliant panels that maximizes the product of selection probabilities. If you run this on the climate assembly UK data, you get the histogram at the bottom, which looks a bit smoother than the one at the top. So from that viewpoint, might look a bit nicer. But Leximin actually has a significant advantage over Nash welfare in that it's pretty easy to explain. Because the first thing it does is it basically makes the least happy volunteer as happy as possible. And that's something that's very intuitive both to organizers and to participants in citizens' assemblies. So let's keep this idea in mind of kind of looking at the minimum probability and maximizing that. And I want to revisit the question of how bad the greedy algorithm is. So you might still be suspicious, and you might think, well, I just went so far with this running example of Climate Assembly UK, maybe I cherry-picked that example, and things actually aren't that bad on other examples. So to put the last nail in Greedy's coffin, I want to show you this figure that's based on 11 different data sets from 7 different organizations that we've collaborated with. So there are 5 data sets, 5 assemblies from the Sortition Foundation based in the UK, one from the Center for Climate Assemblies based in Poland, in fact, one from Healthy Democracy, which is American, one from Mass LBP in Canada, Nexus in Germany, Off-by-4, which is American, and New Democracy in Australia. For each one of them, the purple bar is showing K over N, the size of the panel over the number of volunteers. This is the ideal equal selection probabilities that are infeasible, just as a benchmark. In yellow, this is the minimum selection probability under Lexemin. And in blue, it's the minimum selection probability, actually a generous upper bound on it, under the greedy algorithm. And what you can see, or really not see in this figure, is that most of the blue bars are essentially invisible. And that's because in 9 out of the 11 instances, the minimum selection probability under the greedy algorithm is very, very, very close to 0. Even on the 10th instance over here, the greedy algorithm is still doing very badly. So I think this kind of pretty decisively says that if you care about this issue of fairness in terms of selection probabilities, you really have to be careful about how you do the optimization and kind of take this more global optimization approach where you look directly at distributions over assemblies. Now, computationally, it's quite difficult to compute these solutions like Lexemin, Nash welfare, and others. Just think about the set of possible assemblies is gigantic. If you think about 110 assemblies selected out of 1,727 volunteers, there's an inconceivable number of options. And here we're optimizing over distributions over the set of assemblies. So this is really a space that's like difficult to even think about how large it is. And yet we are able to precisely solve these optimization problems using an optimization framework that has some novel components. And it's able to tackle a wide range of objectives, including Lexemin and Nash welfare and a couple of others that are of interest. So I won't go into the details. It suffices to say that we have implemented this algorithm, and that's led to an open source, not-for-profit online platform called Panelot, which stands for Panel Selection by Lot. What Panelot does is it takes as input an instance of our problem, which is the features and the feature values, the pool of volunteers, the panel size, and the quotas. And it outputs the Lexemin distribution over quota-compliant panels. So the first version of the algorithm, which at the time was just doing Maximin, not the full Lexemin, was deployed in April 2020. And it was immediately adopted by the Sortition Foundation, which were our collaborators in this work. And since then, they've used it to select dozens of assemblies around the world, including, for example, a national climate assembly in Scotland, and also the last iteration of the Permanent Citizens Assembly in Belgium that I mentioned before. But since then, the algorithm has been adopted by many organizations around the world, especially in North America and Europe, and I'm showing some examples here. More recently, people have just been using it directly through Panelot, so in many cases, they don't even coordinate with us when they run the algorithm. Okay, so I want to show you 3 additional specific examples of applications of the algorithm because they illustrate another aspect of this approach. So these are examples of assemblies where the organizers decided to visualize the selection process, visualize the randomness in the selection process. The first example of this was an assembly in Michigan, it was virtual, in 2020 to discuss COVID-19 policy, organized by Off-by-4, an American-based organization. And Off-by-4 really put on a show around the selection process with the idea of making the whole process in the assembly more trustworthy and more transparent. So what they had was they had the presenter draw lottery balls from the containers here. So you can see a short clip here. Each of the lottery balls is labeled with a number from 0 to 9. And when the presenter draws 3 lottery balls, he gets an ID number between 000 and 999. And that is the ID number of the panel that's selected out of 1,000 possible panels. So this idea was adopted more recently in Montrose, Colorado, for an assembly to talk about childcare solutions in the city. So they put on this really fun show with kids drawing lottery balls. They had a teen band, so really cool stuff. And most excitingly, there's a national assembly happening in Germany right now to talk about nutrition. So the selection was done a couple of weeks ago. And what you're seeing here is the president of the Bundestag, the German federal parliament, drawing lottery balls in the same way from a distribution computed by our algorithm in order to select the winning assembly that will kind of inform policymakers about this issue. So this is kind of one way to visualize randomness using lottery balls. There are many others. So here's another example that I like. Here, the idea is to use a Wheel of Fortune kind of approach. What you're seeing on the left is 1,024 possible panels, each of which is represented by one of these squares. And specifically here, we're taking the viewpoint of one of the volunteers, and I'm marking in red the panels that this volunteer is on. So the idea is that the volunteer will be able to easily follow the chances of being selected while the process goes on. And what we do is at every point we spin this Wheel of Fortune, which tells us which corner of the grid to focus on. Right? So we initially get southwest, then northeast, so we focus on the northeast of the remaining grid, then southeast, and we need 2 more spins. So southwest, and the final spin gives us northeast, and we end up with a single square, a single panel that happens to be one that our volunteer is on. Okay, so that's another way of doing it. Again, you can use other methods. For example, our collaborators in Poland actually told us that people here would only trust dice as the method for randomness, nothing else. But you can think about many other ways of visualizing the randomness. Now, an important point is that whatever the method you want to use to visualize the randomness in this way, you really need a distribution over panels. So this will not work with a greedy algorithm. It really requires an explicit distribution over panels. But it doesn't require just any distribution over panels. It requires a uniform distribution over a small number of panels. So what do I mean? If you think about the lottery balls examples with 1,000 panels, essentially what you have is a list of 1,000 panels. And the lottery balls select uniformly at random among these 1,000 panels. So in other words, if you have T panels in your list, what you need is a distribution which assigns probabilities that are multiples of 1 over T. Okay, multiples of 1 over T because panels can appear on the list with duplicates, but you need multiples of 1 over T as your selection probabilities. So this is a very significant constraint on the structure of the distribution, the structure of the probabilities. And you might worry that imposing this constraint would harm fairness, would degrade the fairness objective. But it turns out that that's not the case, both in theory and in practice. The fairness objectives are not significantly degraded when you impose this constraint. So in theory, we can show the following result, that for any distribution over feasible panels of size k, we can construct a uniform distribution over T panels such that each individual selection probability differs by at most k over T. Now, notice that k over T can be made to be very small. K is the size of the panel. We saw that in national examples, it's typically between 100 and 150. T, if you think about the lottery ball example, was 1,000 with 3 lottery balls, but it would be 10,000 with 4 lottery balls or 100,000 with 5. So this is something that you can very easily increase by just adding a couple of more lottery balls. So this can be easily made to be very small. If you think about this a bit, you'll see that this directly implies that the difference in the maximum objective is also at most k over t. And you can also draw conclusions for Nash welfare, but that requires a bit more work. So this is in theory. In practice, as these things often are, it's even better. So what I'm showing you here is, again, the 11 instances that we've seen before. For each one of them, like before, yellow is showing the minimum selection probability under Lexeman, and blue is showing the minimum selection probability under the constrained version of Lexeman that is constrained to output a uniform distribution over 1,000 panels. 1,000. And what you can see is that the blue bars are essentially identical to the yellow bars. There's essentially no difference, or a tiny difference between the blue and yellow bars, which means that the loss in fairness is tiny. The purple bars are showing what happens when you plug in the parameters of each instance into the theoretical guarantee. And you can see that even the theoretical guarantee is significant in most cases. But again, in practice, the difference is really tiny. The loss in fairness is very tiny, which means that there's really no trade-off between being able to visualize randomness in the way that we discussed and this fairness objective. Okay, so the last thing I want to discuss is kind of taking a different viewpoint on the question of what fairness means in citizens' assemblies. And what I'll do is I'll denote the size of the population by M and the number of letter recipients by R. And the question is, what's the probability that a person from the population makes it to the set of letter recipients? Well, that probability is R over M, because we select R out of the M people uniformly at random. Now, what's the probability that a letter recipient, somebody who was invited, opts in and joins the pool of volunteers? So that's definitely more complicated. But what I want to assume is that there is such a probability, Qi for person I, that depends on the features of person I. As we saw before, these probabilities really depend heavily on the features, like we saw that the education feature or position climate change very significantly impact people's opt-in probabilities. So let's say that we have these probabilities Qi that depend on the features, and moreover, we're going to assume that these probabilities are known to us for now. If we have that, then what we can do is we can choose our panel from the pool of volunteers with probabilities proportional to 1 over Qi. Okay, so essentially what we're doing is we're reversing the opt-in probabilities at the stage where we're selecting the panel. And what happens is that the Qi and 1 over Qi cancel out. And overall, what you get is that the end-to-end probabilities of people from the population making it all the way to the panel are roughly K over M, which is the kind of idealized selection probabilities that we had in the very first infeasible sortition pipeline. Right? The one where we just select K people uniformly at random from the population. So this is cool. And of course, the question is this feasible? Is this practical? So we have some preliminary answers that I think suggest that this might be practical. In theory, we can show the following result, and I'm stating it very informally here. So as R, the number of invitations, goes to infinity, with high probability, with probability that goes to 1 as the instance grows larger, it's possible to find a distribution over panels of size K that satisfies the following two properties. And here I'm kind of stealing terminology from fairness in machine learning. So we have an individual fairness property, which is essentially what I talked about on the previous slide, that the individual selection probabilities are roughly K over M. And then the second property is a group fairness type property that says that the proportional quotas are satisfied for each feature value, okay, based on the representation in the population, up to an error which equals to the number of features. The number of features, as we saw, can be 7, like in Climate Assembly UK, but more typically it's like 4 or 5. So we get the proportional quotas up to an error which is not large. Now, there's an asterisk in the theorem statement, and that's because this is assuming the opt-in probabilities are known. So this is applying an algorithm that has access to the opt-in probabilities. We worked quite a bit in order to show that we are able to estimate the opt-in probabilities. I'm not going to go into details. I'll just say briefly that there is a small challenge in that we only have access to positive examples. Because when somebody opts in, they give us their details. But when somebody opts out, we don't know anything about them. So we have only positive examples. That by itself would not be enough to do anything. But we also have access to a background sample from the population. And with the positive examples and the background sample, it's possible to leverage kind of off-the-shelf techniques in order to do this kind of learning and get results that I think are pretty satisfying. Now, of course, something that might be worrisome about this feature is this theorem, is that it's asymptotic. It happens in the limit, and you might worry that this wouldn't hold in practice for real-life instances. So again, it turns out that these guarantees and the algorithm work well in practice for real-sized instances. So to illustrate this, let me show you this one last result. This is based on the Climate Assembly UK data and the European Social Survey, which is a large survey in Europe, obviously, that gives us the background sample. And what we've done here is we first used these two data sets to estimate the opt-in probabilities. And then we simulated the whole process end-to-end. So we created a synthetic population of millions of people, and we kind of sent the invitations uniformly at random. We kind of simulated opting in based on the estimated probabilities, and then we ran the algorithm to select the panel. And what this is showing is on the y-axis, the selection probabilities of the volunteers shown as multiples of k over m. So 1 on the y-axis is the ideal thing. It gives you k over m. And the x-axis is the opt-in probability, qi. So this is just really meant to spread out the different points, the different volunteers, different people in the population, sorry. And what you're seeing in blue, the blue dots correspond to the greedy algorithm. So you can see that these blue dots are kind of spread out. They're not really concentrated around the ideal of k over m. Whereas under the new algorithm in yellow, the one that's implicit in the theorem from the previous slide, you can see that the points are very nicely concentrated around k over m. This tells us that, even though the theorem is asymptotic, the algorithm still gives that kind of guarantee on realistic instances in terms of their size. Okay, so I want to conclude with a take-home message. It's going to be a bit corny, but bear with me for a minute. The take-home message is that we, all of us, with the techniques at our disposal, can play a role in improving the practice of democracy and potentially in shaping its future. Now, one reason why I think this is interesting is that if you asked me maybe around 2015, I would tell you that it's very difficult to impact the practice of democracy because of tradition, because of short-sightedness of voters, for example. And the killer app of the area of computational social choice is helping small groups of people make smart collective decisions. And indeed, in the applied work from a group at the time, we focused on creating kind of not-for-profit online platforms to help people make joint collective decisions in areas like voting and fair division. But what I've realized in the last couple of years is that we can actually impact the practice of democracy using these techniques, right? Using mathematical approaches, algorithms, and AI. So, this is, of course, one example, but there are many other examples that I think are inspiring. So, for example, participatory budgeting is one of them. Cities that are kind of have their residents vote over how to spend part of the budget. This is happening on a very wide scale around the world. And there's beautiful work, for example, by Dominic Peters from CNRS in France and Piotr Skowron, who's here in Poland, who developed a beautiful method called the method of equal shares that gives amazing theoretical guarantees and is now adopted in several cities in Poland and Switzerland and is gaining wider adoption. So this is just one example from participatory budgeting. Another inspiring example is work in the US on political redistricting and preventing gerrymandering. There's an amazing body of work by people like Munduchin from Tufts, Jonathan Mattingly from Duke, Kosuke Ime from Harvard, Wes Pegden from CMU, and so on and on, who have kind of used math and algorithms and statistics to shape the discussion around redistricting, and these results have played a role in a lot of high-profile court cases and in the current round of redistricting that's happening right now. So I think all of these examples really suggest that we can impact the practice of democracy. To me, that's incredibly exciting, and I hope it's exciting to some of you as well. So I want to finish with bibliography. The so most of the talk up to Panelot was based on work with Bailey Flanagan, Paul Gueltz, Anupam Gupta, and Brett Hennig that appeared in Nature in August 21. The work on visualizing randomness and transparency is based on work with Bailey and Greg Kinney in NeurIPS 21. And the work on kind of end-to-end probability as the end was based on work with Bailey, Paul, and Anupam in NeurIPS 20. Since then, we've written a couple more papers on sortition, and I'm happy to talk about them offline. I wanted to give you 2 more references just for fun. So if you want to see the same story told, I think in a fun way, with a lot more about the history of sortition, you can check out this article in Scientific American from last year, which also includes really beautiful illustrations by the graphic artists at Scientific American. And finally, if you want to know what's happening right now, 2 weeks ago, we published this opinion piece together with Liav Orgad, who's a law professor in Israel, where we advocate a randomly selected constituent assembly in Israel. So this is an assembly to form a constitution in Israel for the first time. For those of you who may have heard, there are also some Israelis in the audience. There is basically a constitutional crisis in Israel. Israel does not have a constitution, and there's a big debate around it now. So the proposal is to form a randomly selected constituent assembly that would create a constitution for Israel. It's something that we're trying to advance, and hopefully we'll see some progress in the coming weeks. That's it. Thank you very much for your attention.
Thank you very much, Ariel, for such a great talk. We can take questions. We have some time, so I suggest people queue for the mics that want to ask questions.
Hi, thanks for the good morning talk. We have fun here, apparently. So my question here is about what you did not say. So there is a strong assumption in the work that you presented that everybody's opinion is equally valuable, that anonymity holds, right? And there is this thought in fairness. If there are philosophers in the room, I'm sorry, I think it's Rawls, which says that fairness is about justified unequal treatment, that sometimes people come from different positions, and in order to be fair, you actually need to be unequal. So which would translate here is that not everybody gets the same likelihood to be selected or vote or whatever for reasons of maybe competence, right? Mm-hmm. So I would like that everybody's vote is heard when we are choosing where to go to have a meal, but I would prefer that it is the financial experts when we are deciding where the country is going. So just the question is, as you can guess, how does that play into the sortition?
Yeah, that's a great question. So I think I'm hearing kind of 2 different issues in your question. One about different stakes for people, and one about different competence levels for people. So for stakes, this is something that we've thought about quite a bit. We actually have a paper about that as well. You can definitely make an argument that people with different stakes that benefit to different degrees from the policy would have different representation on the assembly. I actually know of only one assembly where this happened, an assembly in Australia to talk about the rights of indigenous people, where indigenous people were overrepresented on purpose on the assembly. You can also think about other examples, like if you have an assembly about abortion rights, you might want to overrepresent women and so on. But the only example I know of is the one in Australia. The counter-argument is that when we have equal representation, that kind of realizes other ideas, as I said, like equality of opportunity, and the kind of diversity of faces in the assembly, and having kind of the representative structure for the assembly gives it legitimacy. So I think there's kind of an argument to be made in both ways, but certainly, there is one example where this was explicitly taken into account. Regarding competence, I think this is a bit trickier, because again, you could make a case that people with higher competence should be overrepresented. So again, like one issue with that is that you won't have you won't have descriptive representation, which would harm the legitimacy of the assembly in the eyes of many people. But I think there's a more interesting kind of epistemic argument, which is that, let me actually illustrate it by an example that was given to me by Alexandra Martin, who's a political philosopher at the University of Toronto. So she gave me the example of assemblies to talk about AI governance, actually, where they ran some assemblies that included experts. And the feeling was that the conclusions they got from the assemblies were not very novel, because they basically got what you would see in academic papers. Right? They didn't really get very novel viewpoints from having these people get together. Whereas when you have an assembly that has this wider range of voices, including people that we don't think of as being experts, then we kind of have a bigger chance of getting novel ideas into the mix. So I think that's kind of an epistemic argument that says, sure, you can make a case for competence, but there's also a strong case to be made for not overrepresenting people who are more competent.
Have you thought about adversarial attacks by the response from the panel members? So if I answer that I don't care about the climate at all, even though I really care about the climate, I could almost guarantee to get on the panel.
That's another great question, and that's absolutely true. In fact, if you think about the Climate Assembly UK example, the quota there for climate skeptics is higher than the number of climate skeptics in the pool of volunteers. Which means that if you say that you are a climate skeptic, that you don't care about climate change, you're deterministically selected for the panel. So it's something we definitely thought about and something practitioners worry about as well. Notice that this is not something that's a result of the algorithm, it's a result of the quotas. So this is unavoidable regardless of what the algorithm does. However, under Leximin, there are actually more opportunities for this to happen, because what Leximin sometimes does is it takes people basically deterministically. If you have very sharp vision, you might have actually seen that in the histogram where there's a small bump at 1, because it takes some people deterministically, which then allows it to improve the probabilities of people at the bottom, right? So some people who plug in different quotas are taken deterministically and help kind of balance the other probabilities at the bottom. So this is something that is even worse under Leximin and Nash, and that's because they don't penalize high selection probabilities. It's something that we've thought about quite deeply. You can address this with other objective functions that penalize high probabilities, but that comes at a cost to other things. So it's something that is definitely an issue, and as I said, there are ways to deal with it, but not without cost.
Thank you.
So thanks for an inspiring talk. This is cool. Especially this idea of looking at the entire sortition pipeline, I find very compelling, right? So perhaps I missed it, but did you ever talk here or think elsewhere about just the probabilities of sending letters to people? Because that would seem an obvious point of intervention, right? You could equalize things presumably quite a bit. In countries like Germany, a fair number of attributes of citizens should be known, at least theoretically, right? And so therefore, at this point, based on attributes, you could already sort of send more letters to parts of the population where you know that the acceptance probability will be low, as just a very simple example.
Yeah, absolutely. That's a very good idea. Definitely something that we've thought about as well. So I don't know how things work in Germany, but what I do know is that in most countries, you don't have access to that information. So in most countries, what happens is you have a national registry of addresses, and the letters are just sent to these addresses where you don't really know anything about the people getting them. Another common method is random digit dialing, where you're just dialing random digits, obviously, getting random phone numbers, but again, you wouldn't know anything about the people getting the phone calls. You don't have some registry of phone numbers with the attributes of people. So, it might be possible in some countries, but in most countries, it's not feasible to get that information. And that's why the standard pipeline is really sending these invitations at random.
So just a quick follow-up. I mean, that makes sense if you run it sort of outside of the existing political system, right? As soon as, your national parliament supports such things, and you've given good examples, surely their statistical bureaus have access to that kind of information, right? So I'm really wondering whether the whole thing couldn't be a lot more efficient if the governments that are already bought into supporting that idea at the government level were cooperating.
Yeah, that's very interesting because there are many examples of government-run sortition processes for assemblies. I don't know of any examples where that kind of thing has been done. So in all of the national examples that I know, they did follow the kind of pipeline that I talked about. Mm-hmm. Yeah, but certainly, like if you got additional information at the government level, you would be able to do more. Absolutely.
Okay, thanks.
Last question.
Thanks. Fantastic topic. I'm super grateful for your talk. It made me wonder, and by the way, we had a slightly related conversation at the opening of ECML. There was a poster session where people were just passionate about the power of randomization and randomness and what you can do with it. And somebody said, what if we just voted randomly for a prime minister? And that got into a very similar direction. However, this makes me think, you mentioned elimination of the selection bias, because people may not want. So how about, should they be perhaps forced to contribute? Mm-hmm. It may sound harsh at first, but for example, in your country, people have to do military service, whether they want or not. So isn't it a much nicer thing to force them for civilian service? I've done 2 years of service as paramedic in my home country. But it seems, because then you avoid that the power-hungry people end up in politics, right? And that seems to be the core of the problem. So rather than eliminating the self-selection bias as a post-hoc step, should we not even, focus on getting those people into politics to say, no, this is a dirty business, I don't want to have anything to do with it, which is, my motivation for staying out of politics, for example. So that's the one thing. And the second thing is we need to be very careful that we have representation, direct or as proxy, for all stakeholder groups. That would be my way to evaluate how well your scheme works, right? And there are, of course, groups that cannot represent themselves. For example, mentally handicapped people, people who, like children that were actually already aborted, they cannot represent themselves. They need proxies to speak for them, for their values. And therefore, I think this are all stakes represented is a nice way to evaluate, does it really work? But I think maximizing randomness solves a lot of these things automatically, including adversarial attack threats. Mm-hmm. So thank you again.
Yeah, very interesting question. So on the issue of forcing people to serve, I myself served 4 years in the army, so I'm definitely not opposed to it. I think there are definitely kind of political issues with that. Let me give you one example. I think in general, if it was possible to get people to serve in some mandatory way, it would be great. Of course, we have that in the US, for example, with jury duty, right? That's kind of one of the last vestiges of sortition. But one idea that I have read and I really like is a blueprint for how democracy might look like when you have a lot more sortition. And it's by Terry Boricius, who's a political scientist. The idea is composed of many different committees that kind of inform each other in the legislative process, and they are based on volunteers. But where he has mandatory service is when the law is actually ready to be voted on, what he proposes is what he calls a policy jury, which is 1,000 people selected at random from across the US who show up for mandatory service in Washington for a week. And what happens is in this week, they hear about the proposed law, they deliberate, and then they vote on this law. So the idea here is not for all of the different bodies to be mandatory, but when you want to adopt a law or vote on a law, then you have mandatory service for 1,000 people from across the US. So I think that that's kind of it's a fantasy, right? It will take a very long time, if ever, until something like this is implemented. But to me, it strikes a nice balance in terms of how many people how much service there is in this sense, and how much benefit you're getting at a crucial stage from really forcing people to participate.
Great, we can take the rest offline. Thank you so much, Ariel.
Thank you.
you.